So now let's switch gears and look at another very important category of nanomaterials, which is the case where we call nanocomposite yarns. Okay, so we briefly looked at that in the past, and we're going to dive into more details about some of the multifunctional capabilities of these materials and how they're made. The thing is, there are many papers on using these materials for different multifunctional applications, but we're just going to briefly go over some of those because of the limited time we have in a semester. So the building, so if I, so basically the first thing is, if you look at this going from here to here, at the largest scale, they appear like a yarn, any yarn. When you go smaller and a smaller scale, you basically end up getting you end up seeing individual carbon nanotubes. If I load one of these guys, like that and like that, I end up basically stretching carbon nanotubes and also breaking the bonds between carbon nanotubes, such as these bonds. So the building block of these materials are basically, you can think of them as individual carbon nanotubes that do not have to be straight, that there's some overlap between them, and so they are transferring, the load is transferred from one to the other. In a lot of cases, it's only carbon nanotubes and van der Waals interactions, but you could add another polymer as well. Although wetting of every individual junction is a hassle, truly. I just put it here for you to review the concept we discussed in the context of carbon nanomaterials, that really the building block is going to be something like that. And if I stretch, for instance, this guy this way and this guy that way, in that case, this interface between them is the one that's going to be loaded. And we discussed how you can, from these experiments that you load individual junctions, you can get to the strength of the junction, the shear strength of the junction. There are a few methods that these types of carbon nanotube yarns are fabricated. And the first method is kind of pioneered, or Professor Baumann from UT Dallas. He contributed a lot to this work. The first paper on this is a paper in Science in 2004. And so basically, these are, what you see here, are individual carbon nanotubes. Perhaps a better figure of them is here. This, from here to here, is actually from here to here. And so they try to extract a piece of carbon nanotube out of this, and carbon nanotubes will be attached to each other, so one will pull the other, and this process, like a chain reaction, one after the other, like a wave, continues, and you eventually get something like this, and you can weave them into different forms of fibers. When these works like this were published, a lot of the hope is about the time I became a graduate student. A lot of the hope was that the strength of individual carbon nanotubes is very high, is like 10, 20, 50 gigapascal. And the idea was that if I make a yarn like this, can I potentially translate that as strength in a larger scale? Can I see that as strength in a larger scale? Can I make a yarn in a larger scale that has that such high strength? And unfortunately, a lot of that hope didn't materialize. for various reasons, including the shear lag model that I explained, that if you increase the overlap length too much, it's not going to increase the total force that the junction can take. There were other reasons about carbon nanotubes, the defects in them that reduces the strength and so on and so forth. So, so basically, if you look at the side view of a jungle or forest, sorry, not jungle, a forest, you'll see something like this. So carbon nanotubes are not all aligned like that. In fact, there are some carbon nanotubes that go in the lateral direction. And that makes it kind of interesting because those ones that go in the lateral direction are those that allow for this pooling to happen. Look, A, B, C, D. So you're pooling on this side, and there's something that's lateral, that's not straight entirely, and it pools on the rest of the forest, and this process continues. At this point, I would like you to pause this video and go and look at two of the videos that are generated by Professor Bauman's group. These are on YouTube. The links of them will be available to you in the slides that I send you. I will send you. Now, it could be, you could use also a double scrolling, so the two sides are scrolled against each other, so it provides an interlayer like this. Blue and orange are scrolled against each other, so it provides an interlayer that you can use to store any material you want. So, for instance, one of the things they did in this work that was really, really interesting is that they filled these in between the layers. So basically, these dotted ones are the material they filled in between. They filled it with a material that is a superconductor. And so in this case, they basically pretty much managed to get a superconductivity behavior out of this material. So basically, when the temperature goes below a certain value, resistivity almost drops to zero. You can put other functional materials, TiO2 for instance. And what they're showing here is that the specific strength obviously drops because you're adding this functional material that doesn't contribute to the load but adds to the weight. Doesn't contribute to load bearing but adds to the weight. However, the drop in strength is not very significant. So basically, literally, these carbon nanotubes can be used as carriers for other materials to act as multifunctional materials. So basically, you can imagine you can put magnetic particles in them. You can put piezoresistant materials in them. You can store shape memory materials in them and use them as actuators and use them as sensors and all that, and use them as superconductors and all that. So I'm going to stop here and continue in the next slide.